Ladies and gentlemen, to kick things off, please welcome to the stage Tariq Perez.
Hello. How is everyone doing? Yeah, it's post-lunch. I understand that. So welcome to the Container Infrastructure Keynote. This is a new format we were experimenting with for this OpenStack Summit with specific keynote segment for specific focus areas. So we've been having CI/CD keynotes this morning as part of OpenDev. We'll be having Edge infrastructure keynote tomorrow morning in this room. And this is the Container Infrastructure Keynote. Containers are obviously a popular way to consume infrastructure those days. But if you look at production deployments end-to-end from bare metal up to container orchestration platforms, there are a number of unanswered questions, especially if you look at the problem from a security perspective or multi-tenancy. And so to fill those integration gaps, we're encouraging open discussions on this topic during this summit, especially trying to have discussions about security in the open. Security resonates with me personally a lot because I started my open source journey 16 years ago by contributing to the Gentoo Linux security team. And that's why I'm excited with our first speaker, who comes from a company that knows a thing or two about container and security. Please give a warm welcome to Maja Kaczorowski.
Thanks, Terry. Oh, my computer's been locked. That's how secure we are. All right. So my name is Maya. I'm a product manager in security at Google, and I focus specifically on containers. And I'll be talking a lot about isolation today and how isolation works in Kubernetes, because that's what I know pretty well. So what does that mean? What kinds of threats are there to containers? Well, first is the threats that you have to container peripherals, like credential compromise and privilege escalation. This is about how you get the Kubernetes API to do something you might not want it to do. Second category is what ends up running in your infrastructure. You might be pulling images from public repositories or have dependencies on unsupported open source code. If a new O-Day vulnerability is dropped, like today, how do you figure out if you're affected, and how do you quickly patch yourself? And then there are things that we hear people get really, really scared about, which is things like, can you DOS me? Can you DOS my event pipeline? Can you use my container for cryptocurrency mining? And what's usually lumped in the last category as well is container escapes, right? But unlike all the other threats that we're talking about here, container escape is fundamentally different in that it affects containers only. Everything else we talked about affects any system that you're running in, no matter which infrastructure you're on. So I want to point out, though, that container escapes are theoretically possible and doable in test environments, but we haven't seen them in the wild yet. At least I haven't. So if you've seen something interesting in the wild, please come tell me afterwards. What does this mean, and what kind of controls are you going to want to have in place when securing your containers? We have three main pillars following the threats that we had before. How do you develop your applications? How do you manage your images for security? And how do you protect your containers while they're running? So the first category, infrastructure security, is about ensuring that your developers have the tools that they need to build containerized services securely. This includes identity and access management, networking, secret management, and logging, right? Nothing new, nothing that we haven't seen outside of containers. The software supply chain is the middle category here. It ensures about making sure that you know exactly what's deployed in your environment and that it belongs there. This is about securing the host image, the container image, and the code itself that you're running. Lastly, runtime security is about ensuring that your security response team can detect and respond to security threats to containers running in your production infrastructure. And this is extra interesting and cool and where some of these threats come into play. And so what kind of threats do we really have? Well, we have threats from the outside, and we have threats from the inside. From the outside, you might be worried about preventing an attacker from stealing data or credentials or compute time, right? That's what cryptocurrency mining is. You might also be worried about preventing an attacker from altering or disrupting a service. Somebody can DOS your service, for example. Most of the threats that you're thinking about when you think about container security is in this kind of outside category of threats. From the inside, though, You're worried about a different category of threats. You're worried about a process escaping and affecting another process, for example, using shared resources. This is exactly what you're talking about when we talk about container escape. And this is a super interesting concern. So why are we worried about threats from the inside? And is this a reasonable concern? Let's talk about what's fundamentally different between a VM and a container that affects security. For VMs, you have a host OS running on top of hardware. And then you're running a hypervisor on top, which then isolates each individual VM. Each application, its own virtual machine, has its own guest OS, binaries, and libraries. For containers, you have a smaller host OS, and on top of that, a container runtime. The binaries and libraries are separated for each individual app and shared by the applications that require them. So what's different from a security point of view? Well, one is that smaller host OS, right? It's a smaller surface of attack than what you had on a VM, which is a good thing. At the same time, a VM uses a hypervisor, but we don't have that on a VM. On a container. And a hypervisor is something that the industry really trusts and understands, or rather, people who are smarter than me understand how hypervisors work. For containers, the container runtime doesn't necessarily provide the same level of isolation. So I've skipped over kind of all the other pieces because, truthfully, from a security point of view, they don't really matter. It's not all that different. You can take the same constructs that you already know and apply them to containers. So if you want a firewall, sure, have a firewall. You want an IDS IPS, like no problem. You want secret management, like you got it. A lot of the constructs are the same, except for some of the key things we're pointing out here. All right, so with containers, I have a smaller surface of attack. That's a good thing. But I also don't have a hypervisor. So how am I supposed to do isolation? And this is when you're thinking, like, this is so silly. Containers have contain right in the name. They contain. No, they don't. We really, really wish that they did, but they don't. Containers aren't meant for containing. If you remember one thing from this presentation, it's this key message. While containers have great benefits to your development pipeline and provide some resource separation, they weren't really meant to provide what I'll call a strong security boundary. Containers contain like a cup of water, not like a thermos. So you can carry a cup of water back to your desk, a tea, hot tea or whatever, and it'll spill a little bit and you're going to burn yourself. And it's going to suck. Containers are good at containing dependencies. They're not good at containing code from a security point of view. OK, so now that we know that containers don't contain, like, do we even care? Why do we need isolation? The fact is, you might want to be running untrusted code in your environment. So untrusted code, it lives on a spectrum, right? On one end of the spectrum, you have code that is known to be bad. Malware that you're analyzing, you're doing reverse engineering for in your infrastructure. And the other end, you just have code that you just haven't tested yourself. It might be some open source component that you haven't audited. You might also have a project that historically had known security vulnerabilities. You're just a little bit worried about running in your infrastructure. In each of these cases, though, the point is that you don't want the code to affect the security of your own workloads. Beyond untrusted code, there are other reasons you might want isolation. It's just a best practice to follow in terms of reducing the surface of attack of your environment. Or you might be wanting to offer a multi-tenant environment for your customers and make sure that they're separated. Or you might be in a multi-tenant environment and want to make sure you have sufficient isolation from everybody else running there. Applications that run in traditional Linux containers really access resources in the same way that applications which don't run in containers access system resources in the same way that applications that don't run in containers, by making system calls to the host kernel directly. And this kernel runs in a privileged mode, which allows it to interact with the necessary hardware and return the results, right? With traditional containers, the kernel imposes some limits on the resources that the application can access. And this is done through things like Linux C groups and namespaces. But not all resources can be controlled via these mechanisms. And even with those things in place, the kernel still exposes a large surface area that malicious applications can attack directly. So there is a need for stronger, better isolation. Let's talk about a slightly different concept, which is not only is the level of the code, is the level of trust of your code relative, but the trust that you require is relative. So you might not have the same requirements for all the code that you're going to run. The more sensitive the data you process, the more you need to be able to trust the software that accesses it. You wouldn't treat code that doesn't access user data the same way that code that does, or that is in the serving path of your application, or has root cluster access. In a perfect world, from a security point of view, you would access your most critical data only with code that you wrote, that you audited, that you ran some automated security checks on, like fuzzing, And then you would verify that all those checks passed before you deployed that code. Of course, the actual requirements that you have might change depending on the environment, right? So you might be able to trust an open source component if it's running in a test environment for a game app that you're developing in your spare time, but not trust it if it's running in a critical hospital system accessing patient data. So a trust boundary is the point at which your code changes the level of trust, and hence its security requirements. And a security boundary is how you enforce those trust boundaries. A security boundary is a set of controls managed together across all surfaces to prevent a process from one trust level to elevate its trust level and access more trusted processes or access user data that it shouldn't be accessing. At Google, we aim to protect all trust boundaries with at least 2 security boundaries, so that they need to fail independently in order to cross the trust boundary. Traditionally, you might have put untrusted code in its own virtual machine, relying on the hypervisor, like we were talking about earlier, to prevent processes from escaping or affecting another process. A hypervisor is a fairly strong security boundary in that we don't expect code to be able to escape from one VM, go through the kernel, or otherwise go through the hypervisor and talk to the other VM. At Google, we use the KVM hypervisor and put a significant amount of effort into ensuring its security. But what about containers? Well, a container is one security boundary, although it's not a super strong one. It's because compared to a hypervisor, a native OS container is larger, more complex, and has more potential vulnerabilities. You can still use security features, though, like seccomp to help remediate this, but it's still just one boundary. It's not the desired 2 boundaries that we want. OK, so let's talk about isolation in Kubernetes and in containers, and like what you get at each level. So there are lots of different kinds of isolation we can talk about. We can talk about kernel security isolation, which is about the independence of talking to your kernel. Resource isolation, which is how you access shared resources like storage. Service account isolation, which is the identity of the thing that you're running and how it talks to other services, how it identifies itself elsewhere. Control plane isolation, which is talking to, like, for example, the Kubernetes API master and what's restricted. Workload metadata isolation, which is information about your workloads, including the workload name, the workload size. Data isolation, which is the actual data of your workloads. And a network isolation, which is how traffic flows in your environment. That's a lot. OK. Now, let's talk about what actually happens at the levels. Kubernetes has several nested layers, starting with a container, which is not a Kubernetes construct. It's a Linux construct, and building on top of that to give you different isolation, right? The higher up you go, the more isolation you get. So starting from the smallest unit and moving outwards, we have a container. A container is not specific to Kubernetes and provides some basic management of resources. It just doesn't isolate identity or network. And it can still suffer from the noisy neighbor problem of somebody else running on the same node for resources not isolated by C groups. It provides some security isolation, but only that single layer compared to that double layer that we're going for. Next up, we have a pod. A pod is a collection of containers and isolates a few more resources than a container does. At the moment, a pod doesn't have a strong notion of identity, although there are a couple of proposals in the Kubernetes community to provide that in the future. A pod still suffers from the noisy neighbor problem. It gives us more resource isolation and also gives us a bit of network isolation. In Kubernetes, you can use the Kubernetes network policy to provide some microsegmentation. It lets you limit which pods talk to which other pods. It's worth remembering, though, that the network policy is open by default, so please go set that if you haven't set one. Next up, a namespace. A namespace is a collection of pods, and it's the fundamental unit of authorization in Kubernetes. Namespaces provide some control in terms of authorization versus namespace level RBAC, but don't attempt to control resource quota, network, or policies. They allow you to easily allocate resources to certain processes, and they're meant to help you manage how you use your resources, but not necessarily prevent a malicious process from escaping. Since it's the unit of authorization, it gives us the Kubernetes service account isolation, and also gives us a little bit of control plane isolation in that those requests have to be authenticated, so it is dependent on that identity. The node. A node is a machine, either a physical or virtual machine. It includes a collection of pods and has a superset of privileges of those pods. It leverages a hypervisor or hardware for isolation, including for resources. And it's good at that, right? Node has isolation that we're familiar with. It has a hypervisor. It gives us the strongest resource isolation, and we can use traditional networking to isolate the node, including things like firewalls. A cluster is a collection of nodes and a control plane, and this is the management layer for your containers. They offer stronger network isolation with per cluster DNS and provides isolation of metadata in that the cluster won't be able to see another workload's resources name and use, for example. So if you're sharing a cluster with the cookie monster, don't have top secret cookie recipe in there. He'll be able to see that you have that workload. And then the last layer is usually cloud provider dependent. So at Google, we have this thing called projects on GCP, and it's the final layer of isolation. It provides things like project level IAM and org policies. And this is also when you can do kind of the most network isolation with things like VPCs. So I often get asked, like, what do I rely on? Like, if I want to run a multi-tenant workload, what do I actually need to do? Does each person need their own cluster? Do they each need their own node? Like, what am I trying to do? It's a terrible answer, but it depends. The choice that you have for isolation depends on what your workload really needs, right? Like, what you need is what your workload needs. So there's no one-size-fits-all answer. OK, so say you've decided what layer of isolation you're going to go with. Let's talk about sandboxes. You might typically think of sandboxes as a testing environment, something that you use to isolate like tests from prod, and you do some software development in there, you do some malware analysis in there, et cetera. And that's pretty close. We just mean that a sandbox is an isolated environment that can't affect those around it. But you can be running it in prod, too. What's exciting for containers is that containers are all about running different environments together, right? They're about better bin packing what's on your node. So we run sandbox containers. We can start to run things that we wouldn't have been able to otherwise run together on the same node, different environments on the same node that we might have been hesitant to pack together before. Sandboxes really allow containers to reach their full potential in terms of maximizing your resource use. So you've decided to run a multi-tenant environment, and you want to be able to have stronger isolation. Again, like I said, a container might not be good enough in the sense that it's one layer, right? We need a separate layer. We need like a second kernel, for example, a separate kernel. So practically, how do you run a sandbox? How do you run a containerized sandbox? Well, there are great efforts in the Kubernetes community right now to extend the isolation properties of sandboxes to pods. Note I said pods, not containers. And the Sandbox pod API is currently being formalized, but there's still some experimental support already available. The core idea of a sandbox pod is that you can run multiple containers in a pod on a shared node and isolate each pod with having its own kernel that it can use to perform operations. So what are my options? I'm sure some of you are familiar with Kata containers. That's what a lot of you are here for that, I'm sure. First off, so Kata containers was announced in December at KubeCon as a new project combining Intel Clear containers and Hyper-Run V. The idea here is to build a really simple, lightweight virtual machine. Hey, remember, those are good at containing, and using that to contain my workload. The sandbox has a stripped-down guest kernel to limit possible actions. And in this model, each pod is hypervisor isolated, as secure as a VM, and aims to be as fast as a container. It's plug and play with a Kubernetes container runtime interface, a CRI. And I'm not going to dig too deep, because I think you're about to hear a lot more about Kata containers. So ultimately, Kata is aiming to eliminate the need to nest containers inside fully fledged virtual machines, giving each container its own machine with its own kernel and virtualized devices that it can use. Another option is something called gvisor. Gvisor is Google's internal sandboxing technology that was just open sourced a few weeks ago at KubeCon in Copenhagen. Like Kata containers, gvisor is a new kind of sandbox, helps provide secure isolation for containers while being more lightweight than a VM. It also integrates with Kubernetes CRI, making it simple and easy to run sandbox containers. The main differences are around how gvisor runs. The core of gvisor is a kernel that runs as a normal, unprivileged process that supports most Linux system calls. It's not meant to be able to run every single application. Think of gvisor more as like an as a most-purpose sandbox, not an all-purpose sandbox. So we're done, right? We have sandboxes, we have lots of options, we can solve everything. So what's left? Just because you're isolating your workload doesn't mean you're done. You still have a ton of risks. From storage point of view, storage is, if you can pass through data, it's not a security boundary. Networking, remember, you have to still set a network policy, et cetera. And so what's the overall takeaway here that we have? Containers don't contain, remember that, let's not forget. Kubernetes is complex and subject to internal threats. And so if you're going to try to do something multi-tenant, requiring isolation, a bit untrusted in Kubernetes, first pick the right layer of isolation that you need, and then use sandboxes to mitigate risks. So I hope that was a useful crash course in isolation in Kubernetes. Thank you so much for having me.
That was awesome. Containers do not contain, remember that. Containers are also good at packing and density, and we have a lot of people standing up at the back of the room. So I'll ask you to, if you see a seat near you that is empty, just move toward the center of the row so that people in the back can find seating. Thank you so much. Come on, don't be shy. Okay, so when we talk about containers and security, there is lots of excitement around a new collaboration that we launched a few months ago called Kata Containers. Maya talked a bit about it, but to learn more about it and defy the demo gods by running it for the first time in history on stage, we have Bertuccio and Ernst.
All right. Well, thank you very much, Turi. Maya's talk was pretty darn great, right? Yeah, woo! Thank you very much, Maya. It was maybe a little alarming, particularly if the concept of containers don't contain was new to you. You might be sweating a little bit in your seat. We also believe that we need to harden those isolation boundaries. One of the other things we believe is that this needs to be available to everyone, these solutions we come up with. We believe they need to be open source. And so that's why in December, we announced the Kata Containers project. And since then, the Kata Containers community has been working within the 4 opens of the Openstack Foundation. So that is open source, open design, open development, and open community. We've been working on Kata Containers out in the open, and anyone who wants to come along for the ride has been welcomed in. And that's why I am so thrilled to say that as of a few hours ago, Kata Containers 1.0 is now available. Please jump to the next one. Perfect. So Kata Containers 1.0, it delivers an Oci Compatible Runtime, whereas Maya's diagrams were alluding to. Unfortunately, we don't have such cool sketch artists, but we do have some really good designers. So we are wrapping a lightweight VM around each of these containers or pods, and they all have their own kernel. And with that, I'm going to toss it over to Eric for a live demo of 1.0.
Dun, dun, dun. So what I have set up, I think it's set up, it should still be set up, we'll find out in a second, is a 3-node cluster. I kind of have a mix of a few things going in there. I chose a mix of Fedora and Ubuntu. It could have easily been some other distros as well. It's just what I had. And I have a mix of different CRI shims that I'm using. Specifically, I'm using Cryo and CRI Containerd. So for Kata containers, the way that we integrate today with Kubernetes is through these different CRI shims. So what I'm hoping to show is how to set up easily a mixed cluster of running nodes that are using both Run and Kata containers. And just a shout out for VexHost, who is very helpful, Mohammed, for easing my pain of getting a demo and a cluster up and running. It's great. So jumping over, let's see what happens. I hope there's some nodes here. There are still some nodes here. OK. Show you some labels. There's really not too much to see on that. But I really want to add Kata containers on it. So the main thing is this is a running cluster. It knows nothing about Kata. It's never run a virtual machine before, and it makes me really sad. And I want to put Kata on it. So the main takeaway I'm hoping that you get out of this is that security is hard. Installing Kata containers and using Kata containers is not difficult. So with that, I will show you. What do I want to show you? I have a daemon set that I created. I can probably make it just a touch bigger for you. That does 3 things. First of all, it's going to go through on each node on your cluster. So this is 3 nodes. It could be 300. It could be more. And see, what are you running for your CRI runtime? Are you running Containerd? Are you running Cryo? Or are you running something else like Docker Shim? And it's going to put a label on each node. So that way, my next 2 daemon sets can come in, which are actually going to run a Docker file that has a payload in it of different Kata artifacts. There's not a lot. I'll show you later. And install it on that node, such that you can then use Kata containers. So When you say it's hard to install, I say you just do that. And that should be, actually, hold on a second. What I want to show you, if I can type, don't look at me while I'm typing, guys.
I think there's a C.
Oh my gosh.
Be cool, everybody.
You know what I wanted to do. Okay, oh good, we got there just at the last second so you could see what changed. So I showed you the labels before, but specifically what I want you to care about is after installing Kata containers, it's going to add one more label on the nodes that were successfully updated, which is going to say Kata runtime equals true. In this case, we have two nodes, Kata runtime, or container runtime equals cryo, container runtime equals container D. So pretty neat, very exciting. You guys should all be very excited. You can use Kata containers now. So let's start playing with it and run a super amazing demo. I saw a lot of WordPress demos recently, so I decided to go even more exciting and make a guestbook application. So this is just a very standard application available on the Kubernetes website of like, hey, do you want to try Kubernetes? Just do this, and now you can see it working. So if I pull this port, jump over here, cross my fingers, use that port, not this port, you should see something really mind-blowingly exciting. But in this case, Kata is nowhere in place. We just took something off of the internet and applied it. So what I want to do is update what the workload is doing. So what did I just do? Let me show you. Let's update this and look at this. I'm doing 3 things to the running deployment at this point. I am adding some annotations to the YAML file that I already used. So the guestbook has a front end that is essentially what you're looking at on the website. And it has 3 different instances of it that are just using run C today. I want it to run in a virtual machine in case I'm a little nervous about what somebody's going to do. So I have to do a couple of things in this case. One, I'm going to add an annotation. And depending whether you're using cryo or containerd, it's slightly different. It's just opposite logic. Do you trust it? Yes. Do you not trust it? No. It's the same thing, I think. You just got to think that through. This is getting better defined, again, at the sandbox level in Kubernetes, and this should become more standardized so we don't have to remember which inverse you have to apply for an annotation. And then I add one more node selector, which is saying, I want to run this workload, but please, please, please only run this on a workload that has, on a node which has Kata already installed in it. And that was that label that we applied in the daemon set. So please do that. And then for demo purposes, I want to make sure that they run on all their nodes. So I'm spreading it out. That's what anti-infinity does. So let's make sure people are still alive. Everyone's around and available. Let's see what's going on the actual host itself. My goodness, there's QEMU running. What is that about? And if we look at the kernel version, I see that we're running 4.16 on there. Oh, that's not exactly what I want to show. Bear with me. Well, there's 3 instances of QEMU running, 2 of them on Xenial in this case, 1 of them Fedora. So if I'm very lucky, I should be able to go in. Let me open up, because it caches it, I'm going to go to a private window and drop this in. And everyone just cross your fingers, please, that this is going to load. And it does. So now it worked. So at this point, that's really, for getting Kata installed, was kubectl apply. That's it. For updating your existing workload, you can patch it. That's it. One apply. So it's easy. Security is still hard. This is just the bottom piece of it. There's still a lot more above. But as far as the sandbox isolation, you have no more excuses. We can do better here.
And so if you're interested in learning a little bit more about Kata containers, the architecture committee will be giving an update on dresses with pockets. This is really handy. In room 208 today at 3:30. And then if you're interested in becoming a contributor to the Kata project, please join us Thursday at 4:40 in the Lightning Talk Theater sponsored by SUSE to learn how you can become a Kata containers contributor. Thank you very much.
Thanks, guys.
So that was awesome. I didn't know that it was so easy to start and try switching to a secure container runtime with just one command in your existing cluster. It was pretty impressive. To continue, well, I want to say that we have a number of really great open source pieces of technology with Kata containers, with Kubernetes, with Openstack, and the last mile for open infrastructure adoption is really integration between those various projects. It's where the challenge remains. Thankfully, we have smart people looking at that problem, and we have two of them here. So help me welcome on stage Ryu Taro and Craig McLuckie.
All right. Hey, folks. It's always fun to have an opportunity to talk to a community like this. So thanks for joining us. Today, I'd like to give a brief introduction to a technology that we've been working on for a little while. It's a collaboration between Bertuccio, which is a little company that Joe Beda and myself started about 18 months ago, and Yahoo Japan Tapio. And the intent here is to start really bringing these worlds together. So let's just jump in. So the first thing I wanted to say is, like, you've probably all heard the words cloud native. It seems to be almost hit that sort of crescendo of buzzword awesomeness where everyone's talking about cloud native. I think one of the most common misconceptions about cloud native is the idea that cloud native applications are applications that you build to run in the cloud. And when I say run in the cloud, I mean on Amazon or Google or Azure. That's really not the way I tend to think about cloud native. For me, cloud native is about borrowing a lot of the patterns and practices that were pioneered by the internet giants to solve problems at scale. And those patterns and practices apply just as well to the problems that enterprises face on a day-to-day basis. In many cases, enterprises are starting to tackle the challenges associated with internet scale applications as most modern businesses become more intrinsically connected to their consumers through web and mobile properties. As they start really chewing on problems around IoT and increasingly connected devices, those same set of problems exist. But they also exist in terms of the massive heterogeneity of the workloads that enterprises run. And so technologies like Kubernetes and containers have really brought that to the fore and made a new way of operating accessible to organizations of all types and sizes. Now, one of the key challenges that we face is that cloud native doesn't exist in isolation. As you start thinking about what we built with technologies like Kubernetes, the idea there was to really start providing a framework where you could profit from these capabilities, but you could do it anywhere. And one of the beautiful things about the emerging cloud native technologies, things like Kubernetes and Docker and all of the adjacent technologies, is that they work well kind of everywhere. You can run them in your own data center, you can run them at the network edge, you can run them in the public cloud, and they create this incredibly consistent environment to run your applications, and they do it really, really well. I'm sure you're all pretty familiar with Kubernetes by this point, so I don't need to go digging into that. Now, one of the interesting challenges is, like, how do we merge these streams? The reality is, like, greenfield doesn't exist in most organizations. Technologies like hypervisor-based workloads aren't going away. And so it's up to us, the community, to start thinking about what set of assets can we create, what set of technologies can we bring to bear that bring these worlds together and that solve some existing problems that have been there since day one. And so for me, this isn't about displacement. It's about augmentation. It's about creating ways that these technologies work intrinsically better together. And one of the standing problems that we see a lot is, how do you deal with internet scale ingress? The ability to connect a myriad of devices or consumers or other things that are existing out there in the wild in the internet into a blended environment where you might have OpenStack, you might have Kubernetes, you might have a variety of technologies. And traditionally, the types of technologies you use for load balancing have been grounded in the old world. So there's a lot of investments that are made in big iron load balancing technologies. There's a lot of investments that have been made in software load balancing technologies. But by and large, these have really been designed around relatively traditional workloads. Cloud-native workloads have some interesting new properties. They're much more dynamic. They're much more robust in the face of failure. They scale much more rapidly to deal with the needs of modern enterprises. But being able to wire that in so that you can deal with the deluge of information that is emerging is challenging. And as we start thinking about this problem space, there's a lot of need to do more at the L7 level. So if you think about the way that a lot of load balancers have been set up, they tend to run, initially like L3, L4, and they leave a lot of value on the table in terms of application visibility and application level configurability. And again, because a lot of these workloads were built around relatively static configuration models, they don't translate very well to this new world. So the good news is there's a lot of technologies that are emerging that make it easier to deal with this, and we'll be talking about one of those today. So we're going to be introducing a new project, which, as I said, was a collaboration between Octapio, Yahoo Japan, and Heptio, which is a scale-out load balancing solution that's designed to work well in both of these worlds. So you can deploy it on-prem, you can deploy it in the cloud. It works well with Kubernetes and supports the intrinsic dynamicism of these cloud-native workloads. But it also solves some hard problems that exist in the traditional world of virtual machines, where OpenStack has gained a tremendous amount of momentum and traction. At the heart of it, what we've built is a cloud-native load balancer. And when I say cloud-native, I don't mean a load balancer for cloud-native applications. I mean a load balancing system that is designed itself as a cloud-native application. So this is a system that benefits from a lot of the properties that are emerging around cloud-native technologies. It's hosted in Kubernetes. It uses a broad portfolio of the cloud-native technologies that are starting to emerge. And as a result, it's easy to deploy, it's easy to manage, and it's easy to live with. So I'd like to hand off to our friends from Yahoo Japan, who will be talking a little bit more about this.
Hi, I'm Ryutaro Inoue from Yahoo Japan. Let me introduce about Yahoo Japan. Yahoo Japan is a joint venture between SoftBank and Yahoo Inc. Yahoo Inc. was bought by Verizon, but we are still independent. We run many services, for example, news, auction, weather. There are over 100 services. We have 72 billion page views per month and 10 data centers and 100,000 servers and over 50 OpenStack clusters. Most of our services run on OpenStack. Currently, we are migrating our application infrastructure to Kubernetes and Cloud Foundry from OpenStack. Let me explain why we need a software like a gimbal. Many of our services use layer for balancing, so there is a lack of deploy speed. We can't deploy new function quickly enough. And if we found some problems on the deployed version, we can't roll it back speedily. And there is no layer 7 latency visualization. And so we are migrating our infrastructure from OpenStack to Kubernetes now, so we will use both of them for a while. To solve these problems, we need faster and multi-cluster service discovery for both OpenStack and Kubernetes, and Canary deployment with instant rollback, observability, and performance. We want 60 gigabps and 3 million concurrency as the performance values. In order to meet these demands, Gimbal has been released in collaboration with Heptio. Why did we choose OSS instead of bespoke solution? Because we would like users with similar technical issues to collaborate together more effectively. It's also important with this kind of software to be able to easily cooperate with different products. By releasing on OSS, we believe we can deal with a wide range of backend products and easily maintain the code. We want to boost the Gimbal community and make Gimbal more user-friendly. Yahoo Japan will also contribute in various forms. Thank you.
In terms of the conceptual approach that we took to building out Gimbal, as I mentioned earlier, it was a lot easier than it ought to have been because we were building on this cloud-native baseline. We wanted to approach this from a minimalist perspective, create as little technology as we could. We wanted something that was cloud-native but legacy-friendly. And we were also incredibly focused, not just on scaling the number of servers that were under management, but being able to scale the teams, creating a very natural environment where as organizations bring more and more infrastructure to bear, as they bring more applications to bear, as they bring more teams online to maintain them, it became a very natural environment to do that. And so we looked across the technology set, and obviously there were a lot of great technologies already available that we could wire together in a relatively minimalist way. Kubernetes for hosting, which I'm sure you're all familiar with. The Envoy proxy, which has done incredibly well in the community. It was invented or created by the Lyft folks and recently contributed to the Cloud Native Computing Foundation. And then Prometheus and Grafana for increased observability. And what this gave us is, at the end of the day, as I mentioned, a cloud-native environment for load balancing, extracting the load balancing function out of a discrete environment, standing it up in its own cluster, and providing a principled way to start partitioning this across teams and providing isolation of the discrete components. So at the heart of it, there's a few simple pieces that we've put together. The first is a set of discoverers. So these discoverers look inside an environment, and that could be a Kubernetes environment to discover the services and endpoints available, or it could be an Openstack environment. Instead of services and endpoints, we think about load balancing groups and discrete nodes. And those are then propagated into a set of discrete namespaces so that the teams that are dealing with them have access to an environment that's tailored specifically to them and can be configured at the top level by an administrator. And then the system pushes all that down to Contour, which is a minimal Kubernetes ingress controller that Heptio previously contributed, and then wires it into a set of Envoy proxies that are deployed as a daemon set on each of the nodes. And bringing it all together gives us a system that has some really great properties. There's a common point of control. There's a simple, robust environment where it can run. It's easy to add additional nodes. And most importantly, it's cheap. It scales well, and it's incredibly powerful. As we look to the future, we're still in the very early days. I'm a huge believer in delivering technology or building technology, designing technology in the open, which I think is very consistent with the OpenStack values. And with the Gimbal technology, what we released is an early version. We consider it an alpha. And what that gives you is a basic OpenStack and Kubernetes Discoverer components so that you can start running these technologies together. It gives you simple ingress routing. It gives you basic observability. And it's obviously documented. And then as we look to the future, we're going to continue to evolve this. We're going to add multi-team policy enforcement so that each of those namespaces can be assigned to a team. It uses the Kubernetes role-based access control system, so we didn't have to reinvent the wheel. It all ties together very nicely with the Kubernetes toolchain. And over time, we're going to look at a lot of other features. But most importantly, we're going to look to the community to help define and drive this. So if you want to take a look, it's all out there in the open. We invite you to check out the Gimbal project on GitHub. And we look forward to hearing from you, getting feedback. And if you're up for it, push some PRs to us, file some issues. And we'd love to hear from you. Thank you for your time.
Thanks, Craig and Ryutaro. I think it's a great example of what I meant when I said that integration is really the last mile in open collaboration. And but Gimbal is just one way to slice integration between Kubernetes and OpenStack. And our next speakers happen to work on both communities, the OpenStack community and the Kubernetes community. And that's why we will learn from them all the various ways you can use to integrate OpenStack and Kubernetes technologies. Please welcome on stage Dims and Chris Hodge.
Okay, because we're going to listen to this. Thank you.
All right. Good afternoon, everybody, and thanks for coming out. This has been just absolutely beautiful here over the last few days, and we're thrilled to be here and thrilled that everyone can be here. So we're going to take a little bit of a higher level view of the how OpenStack and container infrastructure works together. And we're going to begin by talking about application containers and host infrastructure. to start with, let's go back to 2013 with the release of Docker as an open source project. Docker provides, as you all know and has been talked about in a lot of the other presentations, is Docker provides operating system level virtualization with very lightweight isolation of process trees, network users, IDs, and file systems.
Maybe we should ask them. Has anybody not used Docker?
Has anyone not used Docker before? Is this not familiar with this? And it's so container technology. It's been fantastic. 2015. Kubernetes comes out, and this is open source container orchestration technology. Again, it builds on these abstractions with, to help with deployment scaling and management, with abstractions like pods and label selectors and groups and controllers and services. But one key thing to keep in mind is that Kubernetes is about application delivery. It's very much focused on how do you get applications in a way that is robust and secure, but it relies upon existing infrastructure. Kubernetes isn't interested in delivering infrastructure, it's interested in using it. And OpenStack just happens to be an open source infrastructure system that works very well with Kubernetes. So OpenStack is infrastructure for containers. But what does that mean? Well, in this talk, we're going to kind of cover the entire range of that, starting at the left of this diagram, where we have the bare metal, where we have the servers that everything is running on, how your infrastructure management is deployed on top of that, and then how the consistent open source APIs interact with Kubernetes and Docker to allow you to deliver applications from your cloud. Okay, so let's start with bare metal. So serverless is the next big thing, right? Everybody loves serverless. You're going to run your functions in a container that's running on a virtual machine that's running on hardware. And at some point, you need to be able to manage that hardware. And one of the great things about OpenStack is we actually have a bare metal management system called Ironic. You begin with Ironic to provision your bare metal infrastructure. And you can manage any infrastructure you want with it. It will start by, it manages the entire life cycle of your bare metal. You can begin by discovering your nodes. Ironic has built-in discovery of nodes. And then you can enroll them. You can provision them with different operating systems, and then they're ready to start orchestrating different installations on it. And so in this instance right here, you can see that we have Ironic at the base. We might have a couple of OpenStack installations and maybe even a bare metal Kubernetes installation on top of that, and then layering applications on top of those. One of the great things about Ironic is when it's used as a driver for OpenStack Nova, you actually get all of the APIs that you are used to using for a cloud, and you're able to apply them to bare metal infrastructure. And so this is a theme that we're going to continue to see, that there's going to be an interleaving of the technologies that we're using of OpenStack and containers and Kubernetes and OpenStack kind of layering on top of one another.
Right. I mean, so we're talking about like a sandwich, right? So you can have Kubernetes at the bottom, which you can run OpenStack on top of Kubernetes.
Or a tiramisu, like an OpenStack layer on the bottom, and then a Kubernetes layer, then an OpenStack layer, then a Kubernetes layer, and actually all of them integrating together at these different layers to it's kind of a almost a force multiplier.
Right. So at the bottom, the Kubernetes acts as like an infrastructure underlay. If it's on the top, then it's for end user applications.
Right, and that's also kind of a key thing to recognize is that, for example, on that second layer where you see Kubernetes there, that's not necessarily a user-facing Kubernetes installation. That's where your operators are managing the infrastructure and they're placing applications on top of that then become user-facing. And so it's all about the isolation of. Each layer is providing a different set of isolation and a different entry point that's serving a different purpose.
This is not theory, right?
Yeah.
AT&T was showing some charts about how you can use Kubernetes at the bottom.
Yeah, and this is and we'll actually move on to this. And so, going back to this plot, looking at the infrastructure level, we have an OpenStack installation right there, and one of the most popular ways, OpenStack installers and management systems have moved to using containers as a way to deliver OpenStack. And there are many different installation projects that are out there, but all of them have shared aspects between them. The first is that each is picking a container runtime, whether that be Docker or LXC. They're choosing something where they're building container images for it, which is the next aspect of this, is that each of them will has a set of application images that they build, and then there's some sort of orchestration engine that they're using to do that deployment across multiple nodes.
What are the benefits of using a container runtime to run OpenStack components?
Yeah, so OpenStack is a complex system. If you've ever done any OpenStack installations, it is, a full OpenStack installation will provide you with dozens of different microservices that are each specifically tailored towards handling one aspect of your infrastructure. And this becomes complex. All of them have dependencies. You may want to upgrade them. You may want to upgrade one service before another, which can cause conflicts with your dependencies. And by using a container-based architecture, you're able to contain these dependencies, to be able to, and also have fast and secure upgrades. If you want to do a rolling upgrade, you can slowly route your services. If something goes wrong, you can roll them back.
Different versions of OpenStack components?
You can have different versions of OpenStack running. Okay. It kind of all of the things that you get from using containers in an application layer higher up, you can also apply to the infrastructure layer.
Right.
So there are kind of four main projects that we're showing up here that each shows the different aspect of how these work. For example, OpenStack Ansible uses LXC and LXC-based images in Ansible, where Cola Ansible uses Docker-based images and its own Cola images, and then Ansible for orchestration. O is similar. It uses Puppet and Ansible for orchestration. Mm-hmm. But then the interesting part is when we get to OpenStack Helm, where it's also using Docker images. It tries to be agnostic about the sort of images that it's using. It'll use Cola or Loki images. Loki is another OpenStack project for producing Docker images of OpenStack projects.
Like Cinder, Nova.
Like Cinder and Keystone and Horizon. Each of these is, that attempt to be very small, very lightweight, right, and kind of depend upon the orchestration engine to do a little bit more configuration at deployment time.
Yeah, that makes sense.
But then it's using Kubernetes and Helm charts to perform the installation.
Right.
And so you bring up Kubernetes on all your nodes, you start applying roles that the Helm charts then drop the services onto. And you have at your infrastructure level, full application management.
Right.
Okay, so now that we have OpenStack installed, you've picked one of your methods for doing it. You've deployed your bare metal infrastructure with Ironic. You've chosen a method to install OpenStack, and you've installed it. Right. Now you have Kubernetes and OpenStack, and I'm going to turn the talk over to Dims, who has been leading our cloud provider OpenStack efforts within the OpenStack and Kubernetes community to kind of talk about that work and how Kubernetes and OpenStack work together.
Right. So. If you take a look at where people are using Kubernetes, a lot of people are using Kubernetes in public clouds. And what are they doing in public clouds? They are starting up clusters based on their demand, like 5 to 10 node clusters in public clouds like AWS or Azure or GC, GKE. And what they are doing is they are not just running their applications, they are also making sure that they can use the resources that is there in the underlying cloud in their applications. For example, in AWS, you can use the volumes that is there in AWS for persisting your information for your applications. So we have to be able to allow the underlying resources of OpenStack to be available to all the Kubernetes applications. So that's basically what we are doing. So we talked about the sandwich at the beginning. So at the bottom, you have Kubernetes as the underlay, or you can have Kubernetes at the app layer, right? So here we are talking about Kubernetes and OpenStack side by side. Another example, good example would be if you already have invested a lot of effort in securing your OpenStack and setting up LDAP stuff, for example, right? Then can I use the same infrastructure to secure the applications that I'm running, right? So that is another example of how we are exposing or using the services that are there in the OpenStack layer to the containers that are running in Kubernetes. So a few things that, so this is an effort that is happening in the Kubernetes community. And in the Kubernetes community, what we are trying to do is we want to have a level playing field for all the all the clouds that are out there. And there are working groups and SIG groups that are working on this effort to standardize what the hooks and the patterns that are available to expose the underlying resources. So for example, these are the 6 things that are typically possible for any cloud provider, not just OpenStack. So when you deploy a node, then Kubernetes needs to know that there is a new node. And you should be able to register the nodes, and you should be able to see when the node goes away, for example, right? You should be able to use the load balancers that are there in the underlying system and firewalls too. So then you should be able to do volumes, you should be able to do networking. So those are some of the basic things that are possible. But then what we are trying to do in the effort that we have going on is we want to expand this using well-known patterns in the Kubernetes community, the various controllers that are possible, the webhooks that are possible, and the plugins that are there. Like kubectl plugin is one example. Authentication plugin is one. Webhook is another example. The management key management service is another example. So we can plug in Barbican because we have Barbican in OpenStack, right? So,
the important thing to remember about this is so we talk about Kubernetes as delivering applications, and it doesn't. It's not in the business of infrastructure. But Kubernetes is very infrastructure aware. And the way it's made aware is through these cloud providers. Right. And so cloud provider OpenStack is a driver that gives Kubernetes access to all of these things. Right. Without the cloud provider OpenStack, it's like you're running on bare metal. When you're running with the cloud provider, whether it be OpenStack or any other, you gain access to a lot more information, but a lot more power and orchestration and things happening automatically for you.
Thank you. Okay, so where are we organizing this work? We mainly use Slack in the Kubernetes space, and that's where we organize the work. In terms of the working groups, we have a SIG OpenStack in Kubernetes community, and we have a mirror organization in our community called SIG Kubernetes, essentially consisting of the same set of people. When I say we, I mean the SIG OpenStack is basically consisting of members of the community from various companies that are interested in this work and who have helped a lot in the past as well. So we coordinate the work between the two communities because all of us, there's a lot of us who work on both communities as well. So we published the container builds. We actually had a test version that we shipped last week so that people can try the initial integration. Then we also do integrated testing. We hold community events and evangelize everything that we do. And our Git repository is the one at the bottom, cloud provider OpenStack. So, and information about how to join the mailing list or when our meetings are held, that's the link at the bottom. So we would really want you guys to try the stuff that we have and see if it helps you in your environments.
So we've talked about how OpenStack integrates with Kubernetes, that we have these drivers that are available that are being developed by SIG OpenStack and by the OpenStack and Kubernetes communities. But at the end of the day, what people are interested in, what we want to do is make it easier for you to install and run Kubernetes. And there are a number of different ways to do that. I mean, there are many tools available that are OpenStack aware that will install Kubernetes and will plug in the cloud provider and give you a full installation. Kubadmin, Kudspray, Kubernetes Anywhere, cross-cloud from the CNCF. But there's actually one notable project that is an official OpenStack project, which is Openstack Magnum. And Magnum is a simple API for launching and managing Kubernetes clusters. It's actually broader than that. We'll also launch Docker Swarm and Mesos clusters, but its most popular use is just for Kubernetes cluster. Again, it relies on the cloud provider OpenStack to build all these capabilities into it, and it's being used in production right now. It's at CERN. Many of you may have seen the keynotes yesterday morning, where they talked about how there are more than 200 independent Kubernetes research clusters that are running on top of OpenStack. And Magnum hosted clusters, support everything that you would expect with Kubernetes: federation, cloud bursting between public and private clouds, scaling deployments up. It's a very powerful tool.
So Magnum is typically used in large clusters where they want to segment and start smaller Kubernetes clusters for various.
Yeah, it's a way for as an end user, as a consumer of an OpenStack cloud, you can reach an OpenStack API, and then you can spawn a Kubernetes cluster within your own tenant and have that be available for you.
And then you can tear it down when you're done?
And when you can tear it down, you can do anything. It's a fully managed Kubernetes installation with more features coming too, including upgrades, including control plane isolation. It's Magnum is actively developed, and if you're operating an OpenStack cloud and you want to deliver Kubernetes to your users, Magnum is an ideal service to be able to do that. We had a little demo that we set up to demonstrate this, but we are running short on time, so I think that I may skip the demo. But if you're interested in hearing and seeing more of this, we'd be happy to show it to you later. We were also going to demonstrate the cross-cloud CI project to.
Right. We have the implementation, but we need to test it.
Yeah.
So
to demonstrate, deployment of Kubernetes with Terraform, because we have these other projects too.
Right.
Cross-Cloud is a Kubernetes deployment project that's developed by the CNCF in support of their CI/CD efforts. And one of the things that's come out of this is they have a number of different drivers for all of the major clouds out there, including OpenStack. And they begin by taking this installer, building a high availability multi-node Kubernetes cluster on top of it, and then running the end-to-end tests on it. And then once those are complete, they install other cloud-native projects like Prometheus and CoreDNS and FluentD. And they run all of the integration and functional tests on those too. And you can see that OpenStack on the right column there not only supports Kubernetes, but all of the applications running on top of that. And it's the same for every other major public cloud. And this is all done with full support of all of the OpenStack APIs and Kubernetes being able to take advantage of those.
But what about the code that we write for doing the integration work? Where does it get tested?
So that's a good question. And we are going to turn over our time to Melvin Hilsman, who has been leading the Open Lab effort, which is a community effort for testing not only within OpenStack, but within related projects. And so we would like to please welcome up to the stage Melvin.
Thank you so much. See if we can, my computer locked as well. Get it open here. All right. And sorry about that. So we gave a keynote about Open Lab Monday. And so what we'll do here is just essentially talk about a quick overview of Open Lab, what's available, use cases you might think about doing in Open Lab, some of the stuff we've done since Sydney, and we're going to have a Q&A, but I don't think the format will allow for that. So quickly, what is Open Lab? So our mission essentially is about integration testing, reporting, validation, development of tools and applications for hybrid and multi-cloud environments. And the message of Open Lab is integration and validation, again, of cloud ecosystem tooling, support of hybrid multi-cloud validation, so not just the development and integration, but supporting it, and then also ensuring that we're doing this across communities and across companies. And we do this in a variety of ways. So we have readily available support people and communication channels that you all are used to, like IRC and participate in Slack. We have powerful cross-project gating of code changes via Zool, specifically Zool v3, and collaboration with entities across, again, various industry sectors. And we're proponents of the 4 opens philosophy. So in Sydney, Open Lab was announced, and these were the 5 companies that seeded the effort. And again, as was spoken in keynotes, it's not just about those company logos, but it is about the people who are actually doing the work. And here's some of the pictures of the great community people who have been helping out, and specifically with the cloud provider Openstack and the testing that we do. So I want to give you an idea of what's available in Open Lab. So in terms of hardware, we have dedicated servers, we've got OpenStack VMs, non-OpenStack VMs, we've got programmable network devices, bare metal nodes run by OpenStack, and the environments are shareable, the configurations specifically. It's federated, it's geographically dispersed, so we can do a lot of different types of testing, not just within, something that you may think, oh, I can do this at home in my backyard or my back office, but something you can do across the world. And you only saw 5 logos initially, but as you can see, there's quite a few more people who are already involved in the Open Lab effort. And I want to look at a couple of them really quick. Chameleon Cloud and Cloud Lab, these are 2 of our academia supporters, or supporters from academia. And so Kate is a pioneer in infrastructure cloud computing, if you don't know her. She created the Nimbus project, and amongst her many hats, she's currently senior fellow at the Computation Institute at the University of Chicago. And Robert is a research associate professor for the Flux Research Group School of Computing at the University of Utah. So I'm going to jump out really quick here. And I'm going to go to first Chameleon Cloud. And what's great is that we have an account here as Open Lab, and it's at a high level. So it's not just like any user coming and trying to use Chameleon Cloud, but we actually have what they consider like a project that other users can be underneath. And so, again, let me just log in really quick. Sorry about that little issue there. All right, and so what you see here is we have a few active projects right now. So they give us an allocation of resources for a set amount of time over a set number of months. And we're able to see, if people who request use resources are actually using them. And again, the important part about this is that it's all open source, it's all free. And our main ask is that you make the things that you use the stuff first, but then you make what you're using public to the communities at large. And again, because this is academia, it's very important that people are educated and informed about what's going on. And so one thing to look at here is that, like I said, the configurations are shareable. And we have a number of different things that you could do, but this catalog allows you to take some of the things that you're doing and make it available to other people. And then, again, you as someone who may not have created something but wants to try something out, you can come here and click on this and provision some resources. There's a lot of hardware that is available as well, as I said. And with the hardware tab, you're able to see the different kinds of configurations or things you want to maybe look at to determine some tests that you think you could use Open Lab for. And what's also great about Chameleon Cloud is that it's OpenStack under the hood. So not only KVM in terms of VMs, but also bare metal. So when you use Chameleon Cloud, you essentially are coming to Horizon interface that you're familiar with. And then the other one, again, is Cloud Lab. And same here, we have a high-level account with Cloud Lab that allows us to create additional projects underneath. And so in Cloud Lab, they use these terms called profiles and experiments. So the application catalog is kind of similar, pretty much a one-to-one comparison to profiles here. So you essentially create a profile, and what's great is that you can create these profiles by using icons, so you can visualize them. And as you're creating them, you can set a number of different options for what you're going to spin up and how do you want things to interact and talk with each other, again, is very, you can be very meticulous about how you want to configure your environments, your tests, your experiments, sorry. And what I love about this is when you click Start Experiment, if you have no idea exactly what you want to do, but you know you want OpenStack, OpenStack for Cloud Lab is, it's a first-class citizen. So when you click Start Experiment, the profile that you see amongst all the profiles of all the experimenters is OpenStack. And you just click on Next. You can see that you can select all the way from Juno up to Pike. You can set how many compute nodes you want, different types of hardware, the link speed is very easy to just click Next and get started, or if you want it to be, expressive, you can get down into the nitty-gritty of how your OpenStack deployment is done. All right, so I won't actually deploy anything, but it doesn't take long. Let's jump back into our slides really quick here. All right, so again, what's available for Chameleon Cloud is, like, we have ARM64, Atom, FPGA, OpenStack Bare Metal, the application catalog. There's crazy filtering. I'm not sure if you can see that slide, but again, you can get down to what type of network card, who's the manufacturer of the network card for these devices, because I want to try out some network card specific tests. And then again with Cloud Lab, you can deploy OpenStack very easily and Juno all the way up to master. So the idea is that while we're constantly developing code, everyone's not running the latest and greatest. But if you want to test out, if I upgrade, am I going to run into any issues? If I run into issues, I don't want those issues to surface in master. I want them to happen in some test environment. All right, so the use cases for OpenLab, again, they're very robust. You can talk about all these different architectures, all these different options you have, different types of deployments of OpenStack. And then we have the great project gating from Zool. And what we want to have as some key output is, as a user, you're concerned about an integration and you want to know this integration, what versions of different pieces of these items work together that you guys have tested or we've tested in OpenLab, so you can go and try things out. So since Sydney, as we demonstrated on the stage, we've done multi-architecture Kubernetes using the OpenStack cloud provider for Kubernetes, using Cinder for volume attachment, using Octavia for load balancing. And once you go out and you add this stuff to your cloud, you're ready out the gate to be fully conformant and multi-architecture ready for Kubernetes. And as we stated again, of course, GCE, you would expect to see them there. If GCE is not passing conformance, there's a big problem. and the other cloud right now, of course, is OpenStack, as you can see there. And I wanted to, I did want to try out like a live demo, but unfortunately, I didn't think we would have enough time. But if you go to this super user article about Keystone and Kubernetes, so we did demonstrate, this WordPress thing, but there's a lot of other work also that's going on. And Saverio and Lingshan are two people who have put a lot of effort into Keystone and Kubernetes, and they have a great ASCII demo video that you can watch that will help you understand everything that's going on, and it's associated with that article if you want to try it out on your own. And then for getting in contact to get started with testing, if you visit openlabtesting.org, click on Get Started. There's a really simple form you fill out. If you want to support OpenLab, again, you click on Support OpenLab. There are tabs at the top which are very easily accessible, and you can support OpenLab in any way that you see fit. We would love for you, if nothing else, to come to Freenode and discuss with us. Come to GitHub, work on some of the code, or just simply email info@openlabtesting.org. And that's it. Thank you. Take it.
Thank you, Melvin, Dims, and Chris. Your work is really a testament to the power of open collaboration, collaborating across organizations, but also across communities. This concludes this container infrastructure keynote. Do we have time for questions? Yes.
In the slides that you showed, one of the slides you showed networking plugins. Do you have options to choose different plugins?
Yes, like I said, I can only show a little bit of all the options, the filtering that's available, but it's a very long line of do you want Dell? Do you want specific models of Dell? Do you want again 4-port network devices, 2 ports? Like it's a lot of variation there. Yeah.
And second part of the question is if we want to put our networking plugin in the Open Lab, who should we contact?
Oh, so in terms of a plugin, what we would probably do is I would say go fill out the get started, click on get started, fill that out, because what's great about Open Lab is that we actually talk to each other, and we can try to understand what exactly the use case you're wanting to solve in terms of a plugin. But I don't think I'm probably misunderstanding, but it's not like it's not an OpenStack plugin like VMware or something. Yeah.
Plus the plugins that you choose and run it in Open Lab for sure. Yes.
Okay.
Yeah.
Yes, Contrail networking plugin.
Oh, okay. Yeah. With the testing. Okay. Sorry about that.
Okay. Thank you.
Any other question? Okay, well, this concludes this container infrastructure keynote. We'll have Edge infrastructure keynote starting at 9 a.m. in this room tomorrow morning. In the meantime, have a great time at the OpenStack Summit. Thank you.